Hi, this is lecture part 3 of chapter 3. Uh, Here we are going to discuss quantum theory. So quantum theory is such an important topic, and it is an essential knowledge that we should have to understand the phenomena of energy. So when we say energy, we use the term loosely because we already know the definition. What is energy is? Energy is capacity to the work or transfer heat. But when you go into the basic details of how that work is done by the energy or how that heat is transferred, we have no clue until like early 19th century how this energy is transferred. We just have this wrong. Well, we cannot blame the past generation because they they have their shortcomings, like they didn't have much of the technology that we experience. So all of those things, right? We are just evolving. So by early 19th century, people still have wrong assumptions, based on the knowledge that we currently have. They have wrong assumptions of what is energy is. I'm just going to go over that list. So because right now, thankfully, when I say many times, we are so thankful that we are in this generation, we now know what is an energy is, what it is made up of, and what is its behavior is, what is its nature is, and how to harness it. So for you to understand all of these things, when you hear like, wind energy, solar energy, or electricity, or, like a quantum computing, internet usage using the energy and the transfer of data, all of these things like wireless communication. When you hear all of these things are possible currently because the scientists have proposed quantum theory. The scientists have quantified the energy. The scientists have defined the energy. So scientists identified it. So what we are going to do in this part is understand what the quantum theory is. And let me tell you, this is very crucial topic, and also usually maybe a little bit challenging for some students to understand. Like I have taught this class before here many times, but some students directly get it easily, some students do not. So what I try to do is I try to add extra content every year, and this year I added so much more content because I kind of took this topic as a challenge to make sure each one of my students gets it, because that's a challenge that I want to take on and see how you guys would do, or how I would actually do in convincing you understand what is an energy is by explaining the quantum theory. All right, let's go into the details. So as it states here, early attempts by the physicists of 19th century met with only limited success when they tried to, explain what is energy is, mainly because they were using the classical physics laws that were already proposed, like, first law of thermodynamics or second law of thermodynamics to explain what is an energy is. Those laws, describe the behavior of, mostly used to describe the behavior of macroscopic objects. But when we talk about energy, it is not macroscopic. At least now we know that, but at the time, the researchers doesn't know it yet at the time. So the problem with the classical physics assumption is that the radiant energy, they thought at that time, because they were using the classical physics laws to explain it, they thought that radiant energy was continuous. I'm going to show you next slide what they mean by continuous is, like, without any interruption. Meanwhile, to give you an idea, they thought that radiant energy is continuous, and that could be emitted or absorbed in any amount. So it has no limits, that they thought that it could be released in different quantities depending on matter it is at hand. If you have big fire, it will release more. If it is a large star, if it releases more energy. If it is small star, it releases less energy. Kind of like that. That's what they thought, and it is very logical explanation for early 19th century. However, over the years that we came to understand, that the scientists come to conclusion that the behavior of these subatomic particles are not governed by the same physical laws as the larger objects. So the subatomic particles, whatever they were present in the atom, are having their own rules inside the atom. So they were behaving differently than the larger objects, the macroscopic objects that physicists use to, propose the laws based on a classical physics. So what we are going to do in this part is understand the behavior of the subatomic particles. What is their behavior? We know what they are, and in this, we know what they are based on, so everything we discussed in this semester so far. What we are going to do now in this part of the lecture is how they were contributing to this new behavior of these microscopic particles. So you guys pay attention here at the bottom. I'm including a couple links in this lecture. The web link that you are seeing here is a link to history surrounding basically on Albert Einstein. Basically, that link is giving kind of a fascinating story of the key contributions by Albert Einstein based on year, in what year he contributed what kind of research. That's a fascinating read, and it only takes like 10 minutes at tops. If you read it, I highly suggest you read it. It's just such an inspiration when you read it. He's only 26 years old when the topics that we're going to, when he proposed his theories on quantum theory that we are going to learn. That is just so fascinating to me. He's 26 years old and he changed the world ever since then. Basically, the research on quantum theory is kind of what made Albert Einstein the Einstein is to us, to the world, as the smartest guy. So, if you have time, spend some time reading it. All right. So we are into business. We are going to discuss these microscopic particles. Let's start by paying attention to quantization of energy. So here in the quantum theory, we are focusing on energy and how to understand it. So we already said that classical physics is not useful on these microscopic particles, so it has to be something new. So that something new research came when scientists have tried to explain the behavior of a black body radiation. What is a black body radiation? It is a perfect matter, the ideal matter that absorbs or releases heat from it, or takes heat into it, or absorbs heat into it. So we already, have the idea what is a black matter radiation is at the time. So we already know the matter. So people have used it to do the research. However, the problem started when scientists like Edley, or in the middle of 19th century, named one guy Kirchhoff. So he has trouble in understanding how does the intensity of the electromagnetic radiation emitted by black body, right? When it emitted, it's like depending on the frequency of the radiation or the temperature of the body. Why is that? Because until that time, people believe that it could emit in any quantities, no matter what you supply to it. If a matter is present, it can emit energy in any quantity, no matter what temperature it is, no matter where it is exposed to. That's the belief they had in the past. But it is found that by that time, this black body radiation is emitting energy at different energy levels, depending on what temperature it is exposed to, when it is absorbing heat, depending on what frequency of light it is exposed to, when it is absorbing light. So depending on what frequency of light it is absorbing, what temperature it is absorbing, it is emitting different types of light and different types of heat. So that is something, gives the indication that there's something else going on than the classical physics assumption that energy is continuous. It will emit the same amounts of energy every time if it is the same matter. That's the classical physics assumption. So then came Max Planck. He had his fascinating story of trying to come up with the explanations. He thought it is just disorder of electrons that is causing this different amounts of energy, which is actually not true. No electron disorder would cause the difference in energy of the electrons, difference in energy of the energy release process from the black body radiation. So he come to this idea that energy is not actually continuous. Energy is actually released in pockets of energy. And he said that as, or titled it as a quantum of energy. So he called that quantum of energy is the smallest quantity of energy that can be emitted from matter, or that can be absorbed by a matter. So this is the difference between classical assumption and a quantum theory. Classical assumption is that energy is just continuous. It just releases without any breaks. However, it is not true. It is impossible for nature to be continuous. So what actually happens is energy releases in the forms of pockets of energy. What it means is that because it is impossible to be continuous, energy released in pockets. The easiest way to imagine is here you're looking at the steps, right? You can go up steps in one increment or some increments, or come down the steps in some increments. So just like that, energy is also releases in increments or absorbs in increments, because the subatomic particles are behaving differently than macroscopic particles. In next couple of parts, I'm going to show you why this energy is released in the form of pockets, what it is causing. I know now, but if I say it now, it wouldn't make any sense. So just for now, believe that, just like Max Planck, when he proposed, all he knows is energy, all he knows and proposed, they say desperately, because it is an act of desperation that he said. Most famously, he wanted to disavow everything that he knows until by the time he proposed this quantum theory, he wanted to disavow everything from classical physics that he knows by committing to this new theory, and he doesn't get much support from the scientific community. He proposed that in 1900. He got lots of, let's say, counter arguments. People didn't believe him at the time, so it is in kind of limbo when he proposed this. So he still doesn't know why the energy is released, but he knows that energy has to be released in a quantum of pockets, but not continuous. That's all he knows, right? Now, then came, well, okay, I'm going to spend some time here on his mathematical calculations and the equation he proposed. So he quantized that energy. By the way, when we say quantum theory, basically, that's where this definition comes from. Because energy is released in pockets of energy. That pockets of energy, he titled it as quantum of energy. Quantum is, kind of in English, the meaning is like some small quantity. So he titled it as quantum of energy. So that's why we call this part of science as quantum theory. So quantum mechanics or quantum physics or quantum chemistry. That's how these are all named. So he assigned a energy value to the quantum of energy that he proposed. He said that the quantum of energy is proportional to the constant of frequency. I already told you what is a frequency is when we discussed about nature of light in part 2 of this chapter. Nature of light is wavelength, and wavelength is distance between clouds, and the frequency is how many those waves goes. So I said at the time, energy and frequency are related, and he has proven that energy and frequency are related with a constant as E is equal to h nu, and this is called Planck's Max Planck equation of energy, and h is called Planck's constant. And Planck's constant is something that you have to remember, because you don't know how many times you use in science, not just in chemistry but in physics. So that number has to stick with you. It is 6.63 10 to the power of negative 34 joules. So he's just describing what we have here is what we just already discussed. Energy is not continuous. Energy released in the form of quantum of energies, and he actually proposed an equation how to calculate it using the Max Planck equation. So based on this equation, you can tell that if the frequency is higher, energy should be higher. If the energy is low released, that must have the low frequency, whatever the radiation that occurred out of matter. So because they were related. So that's how he proposed, and I said that I use the word, it is Max Planck equation kind of in limbo because he didn't get much support from the scientific community at the time. People didn't believe that energy is released in the form of quantums because some people, like at least 3 prominent researchers tried to calculate the energy according to his calculation of E is equal to h nu, and they happen to come to a number of energy as 0 when they try to calculate it at the time. So they think that his equation is not correct, and it doesn't have any energy because it is coming out to be 0. So it is in limbo, and he still hold on to his thought that energy has to be released in the form of quantum, otherwise it doesn't make sense. Why when different frequencies exposed by black body and why it is releasing different types of radiation, right? That's what his basis is, based on black body radiation, how it is absorbing and how it is releasing different frequencies of light or temperature. So then came Albert Einstein. Again, I highly recommend you reading this article because textbook discusses basic topic. It introduced basic topics, but it's not giving complete picture. That's why I have to go and dig in. I lost myself a couple of days in trying to get the perfect content to this lecture. So that's when Einstein stepped in 1905, 5 years after Max Planck proposed that energy is released in the form of quantums, and he proposed his equation of E is equal to h nu. 5 years after that, Albert Einstein used the Planck theory. He believed that Planck's theory is right, and Planck's constant is actually close to accuracy of in identifying the energy. So he supported the Max Planck theory, and he devised an experiment based on Max Planck theory to confirm that energy is released in the form of quantum. So he is the one that sealed the deal for the scientific community. So once he proposed this photoelectric effect, and everyone like, okay, we believe now that energy is released in the form of quantum. Since then, we are believing in it. So how it works? So I'm going to discuss this photoelectric effect in next 3 to 4 slides. I have different types of images of same thing because it's really important for us to understand this topic. So he called this experiment as photoelectric effect. So what he did is he used a kind of energy that he called photons because he bought into theory of Max Planck that energy is released in the form of quantum. So he released a beam of light. I just want to call it as beam of light for now. I want to release the actual word used by Albert Einstein in the next slide or the following slide. So it's kind of like, story to you. That's what I'm believing. I'm telling you the story of quantum theory. I'm so excited. So electrons, so he used a light and he knocked a metal surface with a beam of light. It's like, imagine like he using a shooting gun and hitting on a beam of light. So that light is hitting the metal surface, and he connected that metal surface to a voltmeter to read what if it is reading any current. So metal, before shot by the beam of light, it has no current. It is just neutral metal. But once he shot the metal with a beam of light, he started noticing there is a current because there is a flow of electrons are happening going through the voltmeter. So now he explained this by saying that whatever the beam of light he is using is actually a stream of particles that released in the form of quantum of energy suggested by Max Planck, and that energy is causing the electrons of the metal to knock up from its surface and move into the voltmeter. That's why there is a current flow is happening. And he showed this, well, we have this image to explain ourselves. So when light hit the metal surface and it is knocking off the electrons out from the metal surface. So when electrons out, metals are good conductors of heat and electricity. So electricity flowed through these wires through voltmeter and we read the current here. So it's still the deal. Now let me explain this again because this is so important. So he bought into Max Planck theory that energy is released in the form of quantums. Because he bought into it, he set up an experiment called photoelectric effect. So he got kind of UV light, or a beam of light, they called it at the time. I believe it is UV light. So let me stick with the beam of light, whatever the textbook said. So he exposed the metal surface with a beam of light, a high frequency beam of light. So he observed if there is any electrons coming out. So beam of light has no charge, right? Beam of light has no charge. So this is just energy. So he knows that they were releasing in the form of pockets. So those energy are causing the flow of electrons by knocked out by the metal accretion, because beam of light is so powerful energy. So energy is breaking the electrons bonds with its nucleus. So that's how it sees the current. And I highly suggest you read this article. Now, what did actually happen? Again, like I said, I'm just going to use a couple of slides to describe the same phenomena. So when he set up this photoelectric effect in his research, right? It's been done over the series of experiments. He will set up the experiment to counter every argument that comes, right? So when he set up the experiment, he sometimes exposed the metal surface with a low frequency light. And when he exposed the light with low frequency light, those low frequency light couldn't knock off the electrons from the matter. Okay, so we know that there is some attraction. We already know that there is an attraction, electrostatic attractions between nucleus and electrons, right? Opposite charge. So if you use low frequency light, the energy by light particles are not sufficient to break the interactions between electron and nucleus, so no flow of current. So he increased the frequency of the light. So when he does, then those high frequency light, the energy particles, were able to knock the electrons out. So they sometimes are not only able to knock the electrons out, but they also, those electrons are also taking the extra energy any given by those beam of light, and they just ran with it. That we call it as kinetic energy, that I'm going to use at the end of this lecture. So energy can be released in any quantities in any frequency. E is equal to h nu. So he kind of supported the Max Planck theory, and he said that beam of light is really a stream of particles, and these particles of light now called photons. So he bought into Max Planck theory that energy is released in the form of quantum of energy, small pockets. He believed that Max Planck equation H is correct. It is still correct magically. And he called the beam of light as stream of particles. So what do we know about light in the previous lecture is light is a wave. Light travels in wave. And now he said that based on his photoelectric effect experimentation, he said light is basically is also a beam of particles, and those particles we are now calling photons. That's the name that we just gave like maybe recently, like 40-50 years ago, because it sounds fancy, like something like James Bond photons. So he said that each photon must possess the energy given by the equation E photon is equal to h nu. Remember like seeing that equation anywhere? That's the Max Planck equation that he said energy can be calculated using E is equal to h nu. And he, Albert Einstein, gave the thumbs up that, oh, your equation is perfect. Let's go with it. And here I have another article explain what is a photon is. It's a fantastic read to understand more about photon. It's basic information, but you can always learn more. So I highly suggest you to go to this website and read as well. Now, discuss a little bit more about same topic, because this is so important. I want you to get comfortable with this topic of the photons. Now that you know the title, so energy is released in the form of quantum of pockets, and we call those quantum of pockets as photons. So light is basically a stream of particles, which we call now as photons. So shining a light onto, well, what is happening again, we are discussing same, right? If you shine the light with stream of particles, the photons with low frequency, they couldn't knock the electrons out, so no flow of current. Whereas if you expose the light with the high stream of light, high frequency of light, they have the high energy and they were able to knock the electrons out. But they're not only able to knock the electrons out, like I said previously, that additional energy, you know, what does the law of conservation of energy? A law of conservation of mass says that energy can neither be created nor destroyed. So based on that, if you gave lots of, if you expose the metal with the lots of photons, high frequency photons, high frequency light, these are all mean same thing. That's why I'm using different words for it, so that you would know these are all same thing. Let me say it again. If you expose the metal with a high beam of light, or in other words, high frequency light, or in other words, highly powerful photons, these are all mean same thing. Those high frequency light energy is useful to remove the electron from the metal surface, and any additional energy is taken by that electron that is lost or cut loose from the metal and took off to run away with it, because energy can be transferred into one form to another. That you could see it in the form of kinetic energy, and you could actually, you know, calculate what is the kinetic energy as well is. So then we have another equation to explain that phenomena. We already know that energy is equal to h nu. So that energy that released by the beam of light is equal to work required to break the binding energy between electron and nucleus. Not only that, if there is any additional energy given off, that it can be calculated in the form of the additional energy called kinetic energy. Kinetic energy of an ejected electron. Okay, that's all happened, and everything that we discussed happened approximately more than 100 years ago now. It happened in 19th century when Max Planck proposed that, you know, the energy is actually released in the form of quantums in the pockets of energy. And in 1905, Albert Einstein set up the photoelectric effect, and he received the Nobel Prize like after 10 years or so for his work on photoelectric effect, for his confirmation or for his experiment setup, that saying that energy is actually, well, light is actually a stream of particles. Okay, so now, because you know from previous part and this part, from the previous part, you know that light is a wave function, right? You know that because, you know, amplitude is one easy tool to remember from previous part. High amplitude, bright light. Low amplitude, dim light. That's how we know that, you know, that's one easy way to remember that light travels in the form of wave. And of course, there is double slit experiment also to confirm that. Now in this part of the lecture, we said that light is also a stream of particles. So now I'm saying this for the first time. Light is both wave and a particle. So light is stream of particles released from matter, any matter, right? Light is stream of particles released from matter, and the stream of particles are released from matter. It travels in the form of wave. Okay. People have a hard time understand this, that light is both wave and particle. That's why I'm doing my best to send this message across. In the previous part, we said light is a wave, and we have many proofs, including double slit experiment, to show that light travels in the form of wave. Now we know that based on Max Planck's work and Albert Einstein work, light is a stream of particles, and those particles, and one hard thing I guess people have a hard time is, if it is stream of particles, why you don't see you know, them differently. You cannot see them differently because they travel at close to 1 billion meters per second. How do we see it, right? If they were traveling at that speed, we don't have any finite instrument, and I don't think we can get anytime soon to see the individual particles because they travel at about billion meters per second. So that's why we couldn't see it. It looks like, just one particle, but it is actually a stream of particles, and we know that based on photoelectric effect. Okay? So light is both a particle and wave. Particle because there are stream of particles, and wave because it travels in the form of wave, and we have proofs to say that. This all happened 100 years ago, more than 100 years ago. Now, I mean, in my current research, I find that lately we actually have, this is claimed to be the first picture of light as both wave and particle. And I find this very beautiful. And I want to share it with you. So this research is done by Professor Carl Bones, and he is a professor from a university in Italy. So he set up an experiment. This is everything for you to read, and I'm just going to give you a glimpse of it. And if you would like, you could read all of this, or you could go to this website, which is my source, that I basically taken the highlights and pasted here without any of my edits. So this is not my own work. This is, I find it in my research, and here is the source. This is fantastic news article and fantastic research. So like I said, students have hard time believing it, or start a hard time understanding the nature of light, that it is both wave and particle. Now here you have a proof that light is traveling as a wave. Follow my laser here. See wave, how there is high travel and no area, high travel and no area of light, high travel and low area of light, which is a proof that it is traveling in the form of wave. And how do we know it is a particle? Is we have a proof here that from using this experimentation. So how they use this experimentation is they use the laser and they shot the laser through a nanowire. And they created they created a constructor interference waves to make the continuous wave going on in a nanowire, and then they exposed that waves with electrons, stream of electrons, and they use the response of the electrons when they hit the waves to image this picture. So this picture is basically a picture of electrons that when they return, well, when they hit the wave of the light. So they basically reading, let me say it again. So they created wave in a nanowire. So those waves are constant because they are controlling how much of light they were releasing from a laser, how much of radiation they were releasing from a laser. So they already have an idea of what kind of light they have is. So it is a standing wave, which means like it's not changing frequency now because they stabilized it. So if wave is like this, if light is traveling in the form of wave, so it must be interacting differently with electrons. So they exposed those waves with a bunch of electrons. So when these electrons hit the light, so they change the directions if that light contains particles. I'm going to give you a second to understand it. Even for me, it is sometimes it's like kind of a little bit confusing. That's what one of the great professor of quantum mechanics said. If you claim that you understand quantum chemistry, you're not actually understanding quantum chemistry correctly. He is one of the greatest professor. I think it's a Max Planck or some another professor. My student shared that article with me. His quote is that if you claim that you understand quantum theory, you completely do not understand the quantum theory yet, because it is just so complex. And what we are trying to understand here is the basic concept of quantum theory, which is nature of light as both wave and particle. Now let me give another shot at explaining again. If wave is both particle and wave, so according to this experiment where they have controlled the size of the light wave in a nanowire, then they hit that light wave with a bunch of electrons, right? Electrons, and they were trying to read the response of those electrons using a microscope, a highly finite microscope. So if light is a wave, those electrons should look like in the form of wave. And what you are looking here is these electrons are looking in the form of wave, right? And if light does not contain any particle, those electrons should not change their direction. The very fact that electrons are changing their speed differently, and some of them are faster after they hit the light, some of them are slower after they hit the light of different frequency, is the fact that light contains particles. Unless it has some particle, electrons can go through it. If light is just no particle, only wave, light can go through it, no problem, like this. If light is just a wave, electrons can go through it without any problem. But this is not happening. When light is traveling in the form of wave, when electrons hit it, electrons are returning, the electrons are changing directions. So because they were changing directions, we can now confidently say that light actually contains particles. That's why these electrons cannot penetrate through. Electrons are coming back, electrons are returning upon hitting the light. Unless it contains particles, it doesn't happen. If it is just a wave, it cannot stop the flow of electrons through it. So that is how we know that light is both wave and particle based on this recent research. Because electrons are changing directions by hitting the particles of the light, and because these particles are traveling in the form of wave, and electrons are read in the form of wave here. That's the latest research for you, and I hope you enjoy looking at it. This is claimed to be very first image of our proof that light is both wave and particle. What a good times that we are living in. All right. So this is the last problem that we are going to do in this part of the lecture before we conclude. So the question is asking us to calculate the energy in joules of a photon with a wavelength of 5 times 10 to the power of 4 nanometers, the infrared region, and a photon with a wavelength of 52 nanometers, the ultraviolet region, and calculate the maximum kinetic energy of an electron ejected by a photon in part B from metal with binding energy of 3.7 electron volts. All right. So we were given wavelength, and we discussed similar kind of problems in the previous part when we discussed about nature of light, where we define nature of light is related to speed of light as c is equal to wavelength and excuse me, c is equal to lambda v, which means speed of light is a product of wavelength and frequency. So you were given wavelength and you were asked to calculate the energy. All right. So you have two equations now. One says that c is equal to lambda v, and that is what you learned in part 2 when we discussed about nature of light. And in this part of the lecture, we just learned that energy is released in the form of quantum energy, and that you can calculate using the Max Planck equation by saying E is equal to h nu. So you find something in common. In c is equal to lambda mu, you have nu, the frequency, and E is equal to h nu, you have nu, the frequency. So you have something in common, so you can combine these equations by substituting whichever the missing quantity is. That is how you will identify the energy. So that's how you have to play with the equations. So this is going to be our setup. Have c is equal to lambda u, E is equal to h nu. You're going to mix and match these two equations to come up with what E is going to be. All right. Or maybe it is likely more simple than what I'm trying to make it. Once you identify frequency from the speed of light equation, you can take the frequency value and plug it in here and identify the energy by multiplying with the Max Planck constant. That's very simple than I thought. But whenever you're working with this, one of the common issue for student is to not pay attention to the units. wavelengths are commonly given in nanometers. When they were presented, it's a common practice. When a electromagnetic spectrum frequency or wavelength, electromagnetic spectrum wavelength is given, they give in nanometers. So you always need to convert the nanometers into meters using the conversion factor between nanometers and meters. So convert the given wavelength in nanometers to meters using the conversion factor. So you have your wavelength in meters now. So rearrange the equation C is equal to lambda V, so that you have it as frequency is equal to C over lambda. Then identify the frequency. Once you have the frequency value, then you can use the Max Planck equation for the quantum of energy. Then you can use that equation to identify how much of energy of a photon of infrared region contains. That is how you identify. Here you're required to use the two equations because using a wavelength, you're required to identify energy. Right? You are using wavelength, wavelength, not wavelength. You are using wavelength to identify energy. Well, based on how I'm saying wavelength as wavelength, I can now understand that this part of the lecture is already really long, almost 40 minutes already. But I believe it's totally worth it. Now, let me hold on to that. Now, you're asked to identify the energy of a photon with a wavelength of 52 nanometers. Now, let's do that. You just identified how to do that with a different nanometer wavelength. Now you have 52, and it's the same kind of problem. If you can pause and practice it, you convert nanometers to meters, and then you will identify the frequency of it. And once you have the frequency, you use that to identify using Max Planck energy of quantum equation, then you would identify the energy. All right. So once you get that, let's look into the last problem. So last problem says it, calculate the maximum kinetic energy of an electron ejected by the photon in part B. This is part B, and here is the energy that is ejected, okay, in part B, from a metal with a binding energy of 3.7 electron volts. The binding energy is an energy, the electrostatic energy between the nucleus and the electron, the outside electron of a metal. So to break these electrostatic attractions between nucleus, protons, and electrons, you need to apply certain energy, and that certain energy has to be larger than their binding energy. Then only that electron will then only the electron will be removed from the metal. So the question is asking, if the photon has this much of energy, would there be any kinetic energy that acquired by the electron from this metal with a binding energy of 3.7 electron volts? If so, how much it is? So remember the equation that says h nu is equal to Ke plus W. That's what we are going to use, because we know what is the energy, because we just identified what is the h nu is. So we rearrange that equation to W is equal to Ke minus h nu. Well, no, actually we have to rearrange the equation to have Ke on one side and W and h nu on another side. So it has to be Ke is equal to W minus h nu. So W, again, you need to convert electron volts into joules using this conversion factor. 1 electron volts is equal to this many joules. Once you do that, you rearrange that kinetic energy equation. So you subtract h nu and binding energy one from another to get this much of kinetic energy. So for that 52 nanometers of photon, you have about this much of kinetic energy. You know, that number looks really small because it's not that high of a wavelength. It is still ultraviolet region. And it's a different story if it happens to be a X-ray or a gamma ray that you were exposed that electron of 3.7 electron volts with, then it would have a lot more kinetic energy. So it has low kinetic energy because the energy of a wavelength is already low, like pretty low. Okay, that's all from this part of the chapter quantum theory. I do really hope that you had a good understanding of what is a quantum theory is. why people call it as quantum theory, and also understand why it is sometimes sounds tricky or sometimes challenging for people to understand, because it took about 45 minutes just to say that energy is in the form of small pockets. Just that's statement. Because I want to give a maximum chance to you understand this, I spent all the time that I can. I did all my research I can. I included every possible useful information I think is useful to make my point about quantum theory and the uses of it. I hope you enjoyed it. I hope you got inspired by reading about those wonderful researchers, Albert Einstein, Max Planck, and many others. Then feeling as grateful as me about the science and especially for the contribution towards the quantum theory by these professors. It's all from this part. I will see you again in a part 4. From here, it's going to get relatively easier because we understand what's a quantum theory now, and we are going to use this quantum theory knowledge. And for the rest of the part of the lecture, we're going to explain everything based on this part. That's why I want you to get comfortable with this topic. Okay, bye.